A rogue planet, untethered from any star's gravitational embrace, has been caught in the act of voraciously devouring gas and dust at a rate never before observed, marking a groundbreaking discovery in exoplanet astronomy. Officially designated CHA U1107-7626, this free-floating world, located approximately 620 light-years from Earth in the Chamaeleon-the star-forming region, was imaged using the European Southern Observatory's ESO Very Large Telescope (VLT), equipped with the SPHERE instrument, which employs high-contrast imaging to detect faint companions around young stars, or, in this case, isolated objects. Announced in early October 2025, the observations reveal that the planet is surrounded by a circumplanetary disk of gas and dust, from which it is actively accreting material at an astonishing pace of 6 billion tons per second, equivalent to the mass of Mount Everest every few minutes. This growth spurt blurs the traditional boundaries between planets and stars, as the planet's behavior mimics the rapid accretion seen in protostars during their formation phases, challenging astronomers' understanding of how such isolated objects can sustain such intense feeding. The discovery, detailed in a study published in Astronomy and Astrophysics, highlights the dynamic nature of rogue planets, which are estimated to outnumber bound exoplanets by a factor of 10 to 100 in the galaxy, potentially harboring their own formation mechanisms independent of stellar nurseries. The rogue planet CHA 1107-7626, estimated to be between 5 and 10 times the mass of Jupiter, is still in its formative stages, likely less than 1 million years old, and its isolation suggests it was ejected from its birth disk early in its life or formed independently in a sparse region of the Chamaeleon cloud. The VLT's SPHERE instrument, which uses coronagraphy to block stellar light, though none is present here, and adaptive optics to sharpen images, captured the planet's infrared glow, revealing a surrounding protoplanetary disk approximately 100 astronomical units in diameter, composed of gas and dust that funnels inward via viscous accretion. This disk, illuminated by the planet's own heat from gravitational contraction and accretion luminosity, appears as a faint, reddish halo in the 15-micron wavelengths, indicating temperatures around 1,000–1,500 K at the inner edge. Unlike bound exoplanets that accrete from a circumstellar disk around a host star, this rogue's feeding is self-sustained, drawing from the interstellar medium enriched by nearby star formation in Chamaeleon-the, a region 500 light-years across, teeming with young T-Tauri stars. The planet's rapid growth, at rates exceeding those of any known bound protoplanet, suggests it could double its mass within a few million years, potentially evolving into a sub-brown dwarf if accretion persists, a transitional object that defies neat classification in planetary science. The accretion process powering this rogue planet's feast is driven by the interplay of gravity, viscosity, and turbulence in its circumplanetary disk, where gas and dust particles spiral inward, releasing gravitational potential energy as heat and radiation. At 6 billion tons per second, the mass intake rivals that of low-mass protostars, with the planet's luminosity estimated at 10⁻30 ergs per second, thousands of times brighter than Jupiter, fueled by the Kelvin-Helmholtz contraction and viscous heating, as modeled in hydrodynamic simulations published alongside the discovery. The disk's material, likely a mix of molecular hydrogen, silicates, and ices, collapses under the planet's tidal forces, forming a hot inner rim where temperatures exceed 2000 K, vaporizing dust into gas for efficient infall. This super-Eddington accretion, exceeding the theoretical limit where radiation pressure halts inflow by factors of 10 to 100, is possible due to the planet's youth and isolation, lacking a host star's disruptive radiation or winds. Observations indicate the disk's outer edge interacts with the interstellar medium, possibly capturing fresh material from the Chamaeleon cloud's diffuse gas, extending the feeding frenzy. This phenomenon, unprecedented for a rogue, suggests that free-floating planets could sustain growth long after ejection, potentially explaining the abundance of substellar objects in surveys like those from the Very Large Telescope. Rogue planets like CHA 11077626, also known as free-floating or orphan planets, are estimated to constitute a significant portion of the galaxy's planetary population, potentially outnumbering bound worlds due to dynamical ejections from unstable multi-planet systems or direct formation in sparse regions. These wanderers, detected via microlensing surveys like OGEL or direct imaging in young clusters, lack the warmth of stellar hosts, plunging them into eternal cold unless they retain internal heat from formation or radioactive decay. However, CHA 11077626 bucks this trend, its accretion disk providing a temporary stellar-like glow and heat, possibly sustaining subsurface oceans or exotic chemistry if volatiles are present. The planet's youth, evidenced by its disk's infrared excess, places it in the Chamaeleon Wine Association, a 5-10 million-year-old cluster where low-mass stars and brown dwarfs dominate, suggesting it was likely ejected from a protoplanetary disk around a nearby T Tauri star during early instabilities. This ejection, common in simulations showing 10 to 20% of planets cast adrift, allows the rogue to scavenge interstellar material, a survival mechanism that could explain why some free floaters grow rather than freeze. The discovery challenges models of planetary isolation, implying that rogues in star-forming regions might retain disks longer, fueling unexpected evolution. The implications of this rogue planet's devouring act extend to our understanding of planet formation and evolution, particularly in the context of isolated or ejected worlds that might otherwise be overlooked in stellar-centric surveys. Traditional models like core accretion or disk instability assume circumstellar disks around young stars, but CHA 11077626 demonstrates that circumplanetary disks can persist post-ejection, enabling continued growth through accretion. This could explain the overabundance of free-floating sub-Jupiters detected by microlensing, as these rogues might bulk up from interstellar scraps before cooling into dark wanderers. The planet's super Eddington rate suggests a transitional phase where gravitational energy release outpaces radiation escape, potentially leading to a brown dwarf if accretion continues, blurring the planet-brown dwarf boundary defined by deuterium fusion at 13 Jupiter masses. In the Chamaeleon I region, rich in molecular clouds and young objects, such rogues might be common, with VLT's sphere enabling detection of their infrared signatures against the cold background. Future observations with JWST's MIRI could map the disk's composition, revealing silicates, water ice, or organics, hinting at primordial chemistry preserved in isolation. This find, as ESO astronomer Marcus Janssen noted, shows that rogue planets can have dynamic lives, not just drift into obscurity, reshaping our view of planetary diversity beyond stellar bonds. Located in the Chamaeleon One Dark Cloud Complex, about 500 light-years from Earth, CHA 11077626 resides in a stellar nursery teeming with T Tauri stars and protostars, where the interstellar medium provides ample gas and dust for its feast. The region's low density, 10^2, 10^3 particles per cm3, allows the planet's gravity to capture material over scales of 100 AU, with the disk's mass estimated at 0.01 or 0.1 Jupiter masses, sufficient for sustained infall. Infrared observations from VLT reveal the disk's temperature profile, hottest near the planet, 1000 K, cooling outward, consistent with viscous heating and blackbody radiation. This environment, free from a host star's disruptive winds or radiation, enables the rogue's growth spurt, unlike bound planets stripped of disks during migration. The Chamaeleon Association's age, 5 to 10 million years, aligns with the planet's youth, suggesting recent ejection from a disrupted system, perhaps via dynamical instability in a multiple-planet setup. Future ALMA observations could resolve the disk's structure, detecting CO or HCN lines indicative of active chemistry, potentially harboring complex molecules in this isolated forge. The scientific significance of CHA-WEL-WEMO 77626 lies in its challenge to the planet-star dichotomy, exhibiting star-like accretion while classified as a planet due to its mass and lack of fusion. Protostars accrete at similar rates during their embedded phase, but their host disks are circumstellar. This rogue's circumplanetary setup suggests isolated formation or disk retention post-ejection, a scenario rare in observations. The planet's luminosity, powered by accretion rather than contraction alone, could sustain habitability-like conditions temporarily, with internal heat melting ices or driving geochemistry. This blurs definitions. If growth continues, it might ignite deuterium burning, becoming a brown dwarf, a transitional object in the exoplanet menagerie. The discovery expands rogue planet studies, previously limited to cold, dark objects detected via microlensing, e.g. OGLE surveys finding 1011 in the galaxy. As ESO notes, this growth spurt offers a window into early planetary dynamics, potentially common in young clusters where ejections are frequent. Theoretical models must now incorporate interstellar accretion for rogues, predicting a population of feasting wanderers that evolve into sub-brown dwarfs. Future observations and studies of CHA-1107-7626 will leverage multi-wavelength campaigns to dissect its disk and accretion physics, with JWST's NIR spec and MIRI poised to map molecular lines like H2O and CO, revealing the disk's composition and infall rates. High-resolution imaging from VLT's Matisse interferometer could resolve the inner rim structure, testing models of magnetorotational instability, driving turbulence. Spectroscopic monitoring over months will track variability as accretion hotspots flare, providing luminosity curves for mass estimates. Theoretical follow-ups, using codes like Pluto for 3D MHD simulations, will model ejection scenarios and disk survival, predicting if similar rogues lurk in other clusters like Orion or Taurus. Ground-based surveys like Gaia DR4 2026 might detect more via astrometry, spotting wobbles from disk asymmetries. This rogue's feast, as a rare snapshot of planetary adolescence, could illuminate the 10–20% ejection rate in simulations, refining formation theories and estimating the galaxy's rogue census, potentially trillions, many capable of transient growth. The discovery's legacy. Rogues aren't doomed drifters, but dynamic devourers, expanding the exoplanet paradigm. In the broader context of astronomy, CHA-1107-7626's Devouring Act redefines rogue planets as active participants in the interstellar ecosystem, not passive relics. Traditional views saw them as frozen failures, ejected from systems and cooling to below 100K, but this find shows that in gas-rich environments like star-forming regions, they can accrete and evolve, potentially hosting exotic geology or even subsurface habitability if water ices melt under accretion heat. This aligns with microlensing surveys detecting massive rogues, 5 to 20 Jupiter masses, suggesting a continuum from planets to brown dwarfs. The planet's isolation, without a star's UV erosion, allows disk longevity, contrasting bound protoplanets stripped during migration. As exoplanet counts surpass 6,000 in 2025, rogues like this, detectable via infrared excess, could number in the billions, influencing galactic chemistry by dispersing disk material. Tyson's cosmic indifference fits. The universe scatters planets like confetti, and this one's feast is just one verse in the stellar symphony, a reminder that creation's accidents can thrive alone.